Don? We're going to turn now to another topic which I think will be of equal interest to us. The topic is going to be local area networks again. We'll move a little bit from the mobile radio environment. The talk will be about WaveLAN of NCR. The talk will be given by Bruce Tuch, who received a bachelor's degree from Stony Brook, SUNY, and an MS degree from the Technical University of Eindhoven. He joined NCR in 1985 and is project leader within the Wireless Indoor Network Division at NCR in the Netherlands. Bruce?
Thanks, Don, and I'd like to thank Ted for inviting me here. I'm having a good time. It looks like radio is alive and well and living in Virginia, at least for this week. I'm pretty excited about it. I'm going to talk about our WaveLAN, but in an engineering perspective. What am I going to do here today is give you an engineering idea of how we went about interpreting the market requirements to make a product. And the first thing I'm going to discuss is the requirements. That's what you start before you do anything. Otherwise, you're going to really be in trouble, right? And then I'll go on to some physical layer work, then the radio architecture. I'll discuss some of the technology choices that are being made. And then we'll go on and discuss some of the radio link performance issues. Then the LAN performance issues, benchmark testing and measuring compared to other wired LANs, and I'll have some discussion and conclusions. So first, here we are trying to make a wireless LAN, right? So how are we going to do that? Well, the first thing we're going to do is get a requirement. And the most important requirement I had, and we have, is except for the benefits of cordless operation, the end user should observe the least possible difference with standard install wire-based LAN products, period. It's really easy, right? And anything you do that in your trade-offs, that's what you got to look at. So, what else we have? Well, what is a wireless LAN then? Or what is a LAN then? Well, first of all, there's IEEE 802. They know all about LANs, right? And they are making LAN standards charted between 1 and 20 megabit. So the first thing that defines the perception of a LAN is the speed. People always mention speeds. A LAN, data rate, speeds, not ISDN, but a LAN. Another thing about a LAN is that it's a shared bandwidth data packet communication system. It's not a PBX. It is a media where they're bursty in nature, and a person who sets up a LAN and has 2 terminals expects the 2 terminals to use that bandwidth, and they set up 10 terminals, they expect the 10 terminals to use the bandwidth. Shared. Right? And if you take a phone and you give a phone 10 megabit, he's not going to know what the hell to do with it. But a LAN does. And another important here is initial zero infrastructure setup must be possible, because when you go into new technology, you're going to a customer, you're going to somebody, and you say, hey, I got a great system, but to start up, you got to buy this, this, and this, put some wires in the wall. Maybe eventually you're going to have to do that to expand your system, but to solve the small user initially and get them in the wireless market, you have to have a zero infrastructure solution. Okay, so we have our challenge ahead of us, right, to make a LAN wireless. I'm going to go to some of the protocol stuff. And people are surprised when I say, you know, WaveLAN, they're using CDMA, which we're not. Now, I'm going to explain what we're using and why we're not using CDMA. We're also spreading the spectrum. We're hearing a lot about CDMA here, and I'm not an expert in it in terms of the Qualcomm and the Milcoms and all the other comms. But what I do see, it does seem to be showing some promise for voice. Otherwise, there wouldn't be these debates going on. it has a fixed bandwidth per user type application structure to it, unless you get into sophisticated programming of codes as user demands change. And it does require a homogeneous cellular environment, as far as I could tell. When you get into the reasonable processing gains needed for this, you're going to get into some cost premiums paid. And it doesn't have the structure of an accepted LAN protocol. It's a connection-oriented type system. So very early on, it was decided that's nice, but it's not a LAN. So I'll get to the spread part because there's still a rules and regulations requirement and a lot of issues there. What are we going to use as a protocol then? And I'll give you some of the things we've chosen now. I am active in 802.11 and we're working on and forward to on protocol issues. But we are making product and we are making standards also, and they are both important, but one can't wait for the other. Similar to 802.3 is the CMSA-CD. We're using the CMSA-CA, so the CD part is basically gone. The collision detect has been left out because that's the tricky part to implement. When you try to start implementing it, which are possibilities, you see that a lot of times it costs a lot of bandwidth for the various scenarios. Okay, let me give you some of the things about CMSA-CO as that protocol, which is a carrier sense multiple access protocol. It's distributed in nature, which is very important in radio. It has no centralized intelligence, which is nice. You'll see why. I mean, if one terminal doesn't feel good, he doesn't wreck everyone else. Radio channel capture effects does increase the capacity of that protocol compared to a lot of the theoretical work done on wire. It has a known inefficiency depending how you interpret that at high loads. I mean, you probably at the peak loading you're using 50% of the 50% of the total capacity. It has what they call the hidden and exposed terminal problem, which you have to take into account in your coverage area designs, but that's a measurable thing. So, shortly, spread spectrum modulation and the medium access protocol are two separate entities as far as I'm concerned in the WaveLAN product. I separate them. They're separate. What do we have next is, and we're still sort of answering the question of user requirements here in the terms of protocol. Very important is this guy here, I feel, is you're going to have a lot of autonomous systems set up without any type of communication between these departments who want to LAN. And you don't want to go in there and have them somehow have pass control information between each other. So due to the distributed nature of the protocol, we have user-transparent bandwidth sharing if the regions are overlapping. We have a network ID code in the frame, and so if a frame is sensed from another network, it will not be passed up to the upper levels. You do share bandwidth, but you'll share bandwidth if you give him F1 and you give the other guy F2 also. And then you're sharing it always, even if there isn't anyone there. So here we have a dynamic protocol which shares it on the fly as needed. And you just, that's, you know, this is very important, and I'll get to it later in terms of coverage area and contours of building attenuation. Another thing here is the security. What I mean here, and I'll explain it, is the perception of security is very important, so we had to solve that problem. We have to make the product as secure or more than standard LAN products out there today to define security. And we all know if you really put a lot of effort into it, you could put a loop near an Ethernet cable and pick that up really great. So we're going to make it more secure. What we do is basically three levels. The first two are not really robust in terms of security. The first is the network ID, which makes it so frames don't go into the system to upper level MAC layer stacks from someone else. Second is the spread spectrum part, but as we all know, that's, we're not a military system here. You're not going to be able to get the scanner and just pick it up at 900 megahertz. You have to buy another WaveLAN board. And then we have an optional chip, which is a DSSS encryption. So if you really want security at the physical layer, that's the way to do it. And then you're going to have encryption, and at least comparable to non-encrypted LANs, you're in the play there. Okay. I have here a little picture of a scenario of what we're trying to do with a departmental LAN. You have this wireless LAN, there's the server, and they're all hooked up communicating. It's a LAN, you put a card in the board, I'll show you a picture later of it. And it's possible to use a backbone to get into another wireless environment. So initially the zero infrastructure is here. And when you want to get into trying to solve people's problems today where you'll need some infrastructure, that can be done with this type of scenario. So you do it. These don't necessarily have to be on the ceiling. They could be, wired to wireless bridges, and there could be just another PC on the ground there. Using a backbone, which is Ethernet or any standard 802 dot whatever. And in the future, you could be thinking of this as any type of link, so microwave or whatever. I mean, a lot of the technologies we're discussing don't have to be all mutually exclusive. I mean, they could all help each other solve the same problems. Okay, so now we're going to get into the real, let's get into more of the meat of the matter here, right? How we're going to really make the thing. Things I'm always, whenever we're going along, we always have the list of things we have to balance off what the market expects of the thing. So we have a very high dynamic range, which everyone knows. We have to take that into account of capture effects and design. We are using an FCC ISM band, so we have to take into the regulation issues there, interference and data rate issues, delay spread indoor environments, that's a data rate consideration. Physical layer is stochastic in nature. That gives you a hard time to define your performance to customers. And the open physical layer is means that people are going to put it in places they're not supposed to, like inside a metal door or something. And how do you say that's difficult to control conformance? Okay. Now, what I've done is, before we make the board, make the product, now you have to know what you're doing. Initially, we've done in NCR some building measurements. Later on, a lot of people at the same time started publishing a lot, which really is great for me, because then I didn't have to, I wanted to make a product and not do measurements. I did measurements because there weren't any at the time. And when the measurements started coming in, I felt real great. I can investigate, we can put a lot more time in making the thing. We had a rotating transmit station, dipole antenna, a receive base station antenna, and it was going to a spectrum analyzer and computer system, and we measured fading and all types of neat stuff with polarized antennas, and I'll show you some of those plots. Right here is an example of a small supermarket in Holland, because that's where we measured at the time. Just to give you an idea now, out of this was the typical things you've been seeing of the regression lines, and the N is 3 and 4 type numbers. At that time, I also measured things where we had a two-tone correlation test to measure coherence of the channels, the coherence bandwidth to get delay spread type numbers. It came out to about 12 megahertz. At that time, I started seeing delay spread now coming from a lot of the people, from AT&T to Belcor, and it sort of matched this, even though here you're not really knowing what the power delay profile looks like. It's sort of, if you assume Gaussian, you get a sort of delay spread number out of it. But it matched so well, and I said, great, now I could read all that stuff and don't have to measure all that detail. We have our office, was measured also, same way. And here you have a typical structure of an office with these soft partition dividers, and you get a waveguiding down here with the exponent of 2, while if you get into one of these cells, it automatically, look at the enormous differences, it's adjacent. And this is not going up to the ceiling, right? So you get these big differences and fluctuations. And that has to be taken into account in this. It's not a homogeneous environment. So the cellular approach is difficult indoors, I think, putting these cells around and saying, well, the geographical location and the electromagnetic locations are not the same anymore. Sort of isolated from each other. Okay, I'm going to show a slide you saw from Ted Rappaport's work, and I'm going to show it here. Did some work in measuring in Dayton. Again, but what I wanted to show here is that it depends if you're optimistic or pessimistic in nature, what you think about all this. If you look about through the floor type attenuation numbers, if you go from one floor to another, you see, well, you get different type of exponents, and some people say, oh, that's really terrible, and some people say that's really good. It depends. If someone's on floor 1 and 2 and he's optimistic, the engineer is an optimist. He says, great, look at that. People have asbestos in the ceilings. They use this thing. Only about 20 dB attenuation. That's all right. And the other optimist says, great, 20 dB attenuation with 3 floors. I have good reuse. So it depends where you're coming from. It could be, that's the car salesman part. You know, it depends how you interpret the data. What I'm going to show here, and I think you saw, I think it's some procedures in Ted's work. So here is just to give you an office in Dayton. Maybe that'll move out to New Jersey in the future, but right now it's in Dayton. We have contour plots of attenuation with respect to the transmitter here. So then you see again this non-homogeneous structure of the environment causing wave guiding. So the signal down here is just as strong as up there. So if you got to take into account, what are you going to do? How are you going to have a system that handles that? Complicated problem, right? Topology. The ways performance measurements are done till now, what I do is, what is the coverage area? You assume a homogeneous environment, you have an N is 3, you have a certain knee in the curve, and you do all the analysis, and that gives you a pretty good realistic number of what you're going to get. You didn't take into account that if you're in the aisle, it's going to be a lot greater, and some places it'll be a lot less. That's fine, but you shouldn't use that number to make system calculations where if it doesn't work, the system starts choking. That's not good. So, in one way you could do calculations to give an idea to a customer what the coverage is, but make sure that the system doesn't collapse. Now, what also we've measured and we implement due to that, and I'll get in more detail there. In that rotating antenna, we had 2 antennas. One was vertical, one was horizontal, polarized. We had a pin switch in it, and during transmission, we switched one to the other. And the time between the switching was like a half a second. It was enormous. It was a pretty stationary environment, even in that type of time frame. And our frame size is 2.5 milliseconds. Okay. And what we found is a strong amount of no correlation between vertical and horizontal polarizations. It was really, this is the instantaneous power on one, and then on the other antenna when switched over, you see it's really scattered. This is good for diversity, makes a small antenna design. And the average power, the cross correlation coupling, a lot of times was even positive. You know. So due to that, it said, well, hey, you know, I get a small antenna, I get diversity, switched antenna diversity in this way. And you say, well, why use it? And I'll get to it later. We do use spread spectrum, and there is some diversity in that, but in an indoor environment, you can't count on it. You have to take the worst case. If I have an environment with 30 nanosecond delay spread, which is happening in indoors, then how do I get my fading flat, you know, the flat fading margin? And that you do by the antenna. Okay? The delay spread problem in the ISI I'll come to later. So there we have antenna diversity, cross polarized, seems nice. Then you have, just to show you a chart of the fact that it really is a Rayleigh distribution. I mean, we really found the Rayleigh distribution in the indoors. And that's worst case. Some people say it's Ricky and it's Rayleigh. Use the Rayleigh, you're safe, you know. That's the best way to go, because it's just the worst case one. And it's that type of numbers, you know. At less than 3 dB is sort of, I pissed that away in radio. I'm really impressed about the 1 dB can power control stuff, but it's just like the model that we use is very well known in the literature. We have a discrete model. Each of the rays are Rayleigh fading with random phases. And I'll show you how we use that model in our simulator to measure performance. Okay, now we'll get into the product look before we made it. What we wanted is a LAN board that fits into the computer. So the person who plugs this in, plugs the software in, it operates it to the Novell or whatever, and LAN Manager and all the upper level software. So anyone who knows LANs has minimum installation effort. It doesn't look like anything else to them. Just put the board in, put the antenna on the desk, and fly. That's the zero infrastructure, guys. Okay, now I'm going to get into the more of the hardware meat of the matter here. Modulation, spread spectrum. It's a requirement. Number one, that's where you start. I mean, designing everything is just like another Maxwell's equation, FCC rules. As a matter of fact, a lot of the effort you put in the circuit design is more on the regulations than the Maxwell equations. So here we have spread spectrum as a requirement. It does give some suppression to interference to others who are narrow band in that band. In a 100 kilohertz bandwidth, we are less than a milliwatt in terms of power. But that's the life. But what are we going to use it for? Now, the application space we're working in is not military. Interference is stationary in nature. Maximization of processing gain does not translate into a more robust system. And what I mean by that is, spread spectrum military, you have to assume that the enemy there is not nice and doesn't want to help you and all these other nasty things. But in ISM band, they're just sitting around, they're happily waiting. And the more you know about the entropy of the source, the more you know about statistics of the source, the more spectrally efficient you're going to be able to avoid them. It's just a fact. And what we do is try to really understand the nature of the interferers. And I'll give you an example why spreading more might not even help. If I have a burglar alarm system, and NCR definitely, I mean, that's an important thing. We're in retail, and the burglar alarm system's at the entrance of the doors, and you want to coexist. If you spread in the whole band, then that comes into your band. And having a more bandwidth spreading hurts you than if you just maybe took a little hit on that. Get a little less spreading in, and not even hit on data rate, just get a little less spreading in. Get him in the side there, and terming in a military system, called détente, you call them up and you say, hey, how are we going to coexist electromagnetically? And he said, well, that's I want to do that also. Okay, you stay between 902 and 905 and I'll stay over there. Was that right? Fine, shake on it, beautiful. Okay, a 10 dB processing gain is 10 times data rate. I mean, you got to put everything in perspective and really try to understand the source of the problem. It has known robust multipath properties which we're using. Because we have to spread, we're going to take advantage of it. And there are people out there, some short-lived products, the FCC got a little mad at them, frequency hopping or spreading, and the receiver was staying on one frequency, which is really abusing the rules. And that wasn't allowed. There are more subtle ways to abuse the rules, and I'll get to that later. And one is nonlinear modulation and make chip-to-chip decisions. And you do that, not only abuse the rules, but you need a better channel than the data rate. Because you have to have a channel that supports chip rate. Hard decisions on the chips, and non-correlating. Tolerance impulse noise, that's just the nature of the spreading. Noise, impulse noise is wide band, so if you take a hit, you get a few chips out. It depends on the statistics of it, but it has some tolerance. Now, the WaveLAN, what is the specs on that guy? Okay, go through quick for the radio people here, right? 915 ISM band, first thing. Components are out there. In Europe, that's the cellular band, so you get nice and cheap components. We have a 11 megahertz chip rate. It is DQ-PSK modulated with the chip modulation of PSK. So as a vector, the chips are going up and down like 11, chip rate 11 like this, and then we have DQ-PSK modulation filtered. And I'll get to that later, why DQ-PSK seemed to be the best spectrally efficient. And yesterday, talking about the linear modulation and power stages, I really agreed with that. And I'll talk about it. 2 megabit per second is the data rate of the LAN. Sensitivity, and this is assuming an 18 dB man-made noise factor as a margin due to the environment, output power, and the antenna gains of dipole and antennas. It's time to stand up, so I'm going to go real quick. I might have to skip some of these. Transmission block diagram. Data source, data symbol mapping, differential phase encoder, and this is the standard, the way you can make radio, it's amazing, the way you can make radios today is basically just make these blocks, you know, and put them in. But this is the transmission block diagram. We have a max filter correlator and a DQPSK information demodulator, and it's all in the proceedings there, so I just read it. I won't go into details. We don't use a SAW filter. We had some work together with Delft University. We did make a SAW filter. We even have some patents on it, but we decided not to use it because it just wasn't cost effective to compare to VLSI technology at these chip rates and sizes, because you have to get into VLSI anyway when you get out of the SAW. So if you can, try to get everything into the VLSI as soon as possible. This is the output spectrum. It is almost at the 1 dB compression already, so we get this regrowth, but we're a one-channel system, so it wasn't so important. It is possible if you want to get to multiple channels, even with this filtered QPSK, you can do it, and it is a possibility to get quite efficient. And this is much more efficient than doing all these constant envelope stuff. You know, they have a wired main lobes and all this, so this is the way we did it. And there are a lot of ways. I mean, this is for radio people or analog designers. There's a lot of interesting work still to be done, and it can be done. We use a Barker sequence, and I was going to go through a quick. Spreading is the reason you see spreading here is that the bandwidth of this signal is much greater than if it was lasting the whole symbol time. The Barker sequence is because the odd periodic cross correlation is bounded by 1. So it's chosen for that reason, and the robustness delay spread you see, because if you have delay in this interval, is a resolvable path. Just wanted to show you that. A quick block diagram. I have performance at the end, so you're going to have to wait. You know. Right here, it's a homodyne 915 direct conversion INQ. And 1OF noise is important because the spreading information at 0 hertz is not high. The DC coupling isn't needed. It was a very nice design to get into a homodyne type system. Have 5 minutes? That's the way a microchannel board looks. You plug it in. And now I want to get some performance testing in here, and then I'll get out of here, right? We built a simulator to make the VLSI and to really test the VLSI before we baked it to get a first pass success. What you have is an exponential power profile. From that, each of these paths are Rayleigh fading in random phases, so we get an impulse response. We put that into the emulator. We run it through a mock-up, and we demodulate it, capture it with some digital board here, and then go with the VLSI software, which emulates the VLSI on a mapping of 1-to-1. And then we could then check out how our demodulation works, and we find out that it does, right? And here's an example of an INQ, and that impulse response had a delay spread there of 150 nanoseconds, and we see the resolvable path here, and we have a choose largest selection diversity in the echo, which due to delay spreads we have indoors, we're not going to have more than 2 or 3 echoes, so a rake receiver and the complexity of the rake wasn't needed. I have some curves for that. Okay. So that's what the phase diagram and decision region boundary looks like from that impulse response. Looks nice and clean. And here is you have meters here and outage as a function of how many paths you have. You see here as you get into the fringe areas here, increasing the echoes starts not helping much. I'll get into the reason for that. But this is it's in the proceedings. It's taking account Gaussian and Rayleigh fading and taking the probability densities of each of those effects and doing convolutions. It's like adding the dBs for attenuation. And the outage is defined as a certain threshold you go below where the system isn't working well. And I'm almost done. And this is a chart of at a certain, let's say, 70 dB above the threshold of performance, where if I go with a fade 70 dB, I'm not conformant, it's not going to meet my standards. As you get 2 paths or 3 paths, you see you improve, and then you get more paths, it gets diminishing improvement. Because as you get more and more paths, each path energy is going down. And as each path energies go down, and you're not combining with doing selection diversity, you'll see that that is diminishing improvement. So it's a matter of understanding the channel and knowing where you sit here to see that you're getting good effect of that. To wind it up, I'll give you some two more, I got three more slides. One is how we measure up to other, to the performance here. We have a number of LANs, a number of workstations, and the throughput. And this is the total throughput of the system. Okay? So we see here, this is a measure of how we share the bandwidth. I mean, we have different LANs with different user codes. The total system of all those LANs is about the 1 megabit throughput, but each one is a little less because they're totally overlapping. And this is an idea why that protocol is very robust in our environment, and autonomous other users don't have to worry about each other. They share a bandwidth, but that's just the way life is. And if you compare us to what's out there in wire, we do pretty well. WaveLAN, 2 megabit raw data rate. It's 2 megabit raw data rate, ARCnet 2.5. These are raw data rates. And this is benchmark tests that are standard LAN tests. And it gives throughput numbers. So you see how our 1 megabit throughput compares to a 10 megabit Ethernet. Okay? And this is, the reason for this is that the configuration, which is the market today now, is one of the bottlenecks for throughput. And now, conclusion is, and if anyone wants to know more, I'll be glad to talk about it offline, is we need high-speed wireless LANs is clear. I mean, the need is there, and you put anything about our cord, people are jumping to get it. And we have a great opportunity in ISM bands to solve these problems today. And remember, it's a catch-22 situation, not only for radio designers, if you don't get spectrum with the MCC, you can't make anything, but for application people, software. How many applications are going to be there when we get portable computers, whatever you have that are wireless? And now that we have a base for them to work on, there'll be applications out there. And we want to get an open system, and we want to get standard work done. And that'll be it. Thank you.
If there's a question for Bruce Tuch here, we have one of these, pick them at random, questions for Bruce Tuch.
My question is, have you tested the WaveLAN with other radiation sources in this ISM band present? What happens if somebody else is radiating something?
Someone else, you mean another LAN or another?
No, something else.
Something else. Yeah, we do. I mentioned the burglar alarm systems. We had field trials and we coexist with them. We did some analysis of the automatic vehicle location systems and impulse noise, photocopiers, etc.
Does it shut down the LAN?
No. The burglar alarm systems, we don't measure any performance degradation due to the frequency placing of different users. In the analysis of vehicle location systems, worst case scenario is if a mobile is next to the LAN while he's moving by the building and the shielding of the building isn't enough, then once every second when he's polling back to the base station, once every minute for a second, it could perturb the LAN performance. But due to distributed protocol, you know, it just picks right back up.